potential energy repaying machine. Known by their more boring name, rockets. Rockets work by using some of the most energetic chemical reactions humans know about to basically explode fuel in a controlled way. This converts chemical energy into kinetic energy. The exhaust of the reaction is directed outwards, and pushes the rocket away from Earth. By expanding a lot of energy, we are increasing our gravitational potential energy. Which is a complicated way to say that we are paying back our energy debt to gravity. But it's actually a lot trickier than that. When you burn fuel to get into orbit, you lose lots of energy to heat, exhaust and atmospheric drag, so you actually need much more. And you can't just pile a huge amount of radioactive, really explosive, dangerous fuel close to your payload and detonate it. You need a controlled burn, which is complicated and makes your rocket very heavy, which means it has more mass. The more mass something has, the more energy you need to convince it to move, so you need more fuel to lift up your rocket. But if you need more fuel, that means you need more rocket to carry that fuel. But this makes your rocket heavier, thus requiring more fuel, which requires more rocket to carry that new fuel, and so on. At the end of this madness, you need closer to a 100x the weight of your payload to launch Ariane 6. For example, the European rocket will weigh 800 tons and should be able to transport 10 tons into geostationary transfer orbit or 20 tons into medium Earth orbit. But a rocket can only produce so much thrust, so there is a maximum weight, after which it just won't take off. If you add too much weight, it won't lift off. So, you can't just build bigger and bigger fuel tanks. This is the tyranny of the rocket equation, and it means space flight will never become easy. But wait, it gets worse. Getting to space is still not good enough. You're still inside the gravity prison at the edge of space and will crash back to Earth. Staying in space is much harder than getting there. To get to a stable position, where it can stay for a while, a rocket has to reach low Earth orbit. To do this, you need a lot of kinetic energy, which means going extremely fast at an altitude of about 100 kilometers, this is 8 kilometers per second, 28,000 kilometers per hour is fast enough to travel around Earth in 90 minutes. Here, we can use a trick. Instead of flying straight up, we can go sideways. Earth is a sphere, so, if you're going sideways, fast enough even though you're falling towards Earth, the ground will curve away beneath you. So, as long as you're above the atmosphere, about 100 kilometers up, you'll be able to stay up there in orbit. This is what the ISS does, falling around Earth, expending energy from time to time to stay fast enough. If we look at orbits in scale, we see that near-Earth orbit is laughably close to Earth. To deploy, for e.g. satellites, on leave for other planets, requires another round of energy debt repayment. Getting to orbit is the most difficult part of space flight for us right now. For example, if we want to send a rocket to Mars, half the energy is necessary just to get into orbit and the other half for the 55 million kilometers to Mars. Therefore, to be as effective as possible, rockets aren't built in one giant piece. Instead, we use multi-stage rockets. We don't need to carry an empty fuel tank, so rockets drop it. Rockets today shed their boosters and main stage as they ascend, with each successive stage being its own fully contained rocket, complete with its own engine and fuel. Okay, so this is why getting to space is hard.